Today we are going to do section 5.4, which is on page 566. Yep. This is going to be a fairly short section, I believe, where we will do some of the integration that we've learned so far, especially the evaluation theorem. First, let's do example 5.13, where we're going to integrate something. Okay. The problem is fairly straightforward. We're going to integrate a function that has various powers in there. Please look at your book. In this case, we're integrating a function that says t times 1 plus t, which is a quadratic formula that can be each item integrated by the power rule. Actually, it's not a quadratic formula because there's a square root there, but either way, we can integrate this thing by the power rule, okay? And it's fairly straightforward. So please do this problem, example 5.23, as your homework. Now, the evaluation theorem is rather tedious to apply. You just have to patiently get through it and hope that not make any mistakes. Like they show here, there's a lot of fractions, a lot of fractional powers and stuff. But once you get through all that algebra without making a mistake, you will come up with that odd-looking answer, which is still the correct answer. And so that's that. So please do example 5.23 as your homework. And with that, let's look at the next page where it talks about the net change theorem. The net change theorem is just another way of saying the evaluation theorem of the fundamental theorem of calculus, which states that the fundamental theorem of calculus says that if you integrate a function, okay, look at the bottom one right down here. When you integrate a function, then it equals to the antiderivative with the number plugged in from the top subtracted by the number plugged in from the bottom. Now, if you rewrite it slightly differently, now look at the top equation here. That just means the end result, that is f of b, is equal to f of a plus the integral of the derivative from a to b. That's a slight rewriting of the formula. It has a different name. It's called, what is it called? The net change theorem. The net change, is it important? I haven't found the net change theorem to be particularly useful. That is, it's just the evaluation theorem by a different name. But being that the book wants to talk about it, I guess we will talk about it. To talk about it, let's look at example 5.24. Okay, now where you have you are given give me a second. Now example 5.24 says that if you have some function of a velocity for something that's moving along, then what is the displacement? Well, by physics, the displacement is simply the integral of the velocity. So then you integrate it from the time allotment given, which is in this case from 0 to 3, and then you use the evaluation theorem to come up with a result. So that is the same thing we've been doing, right? I think. So please, well, why am I even showing you this? There's not much to it. So please do this as your homework. Example 5.24. Yeah, 5.24, you integrate a quadratic formula, remembering that the integral of the velocity, it will give you the distance. That's the only thing you have to remember about that. So having said that, let's look at example 5.25. Now 5.25 is just like 5.24 with a slight catch, that they want the total distance traveled instead of the total displacement. What happens with the difference is that while you're integrating in both cases, but one of them might have a negative value, the negative distance. That is, you went and then your velocity you start going backwards. Okay, you're going back and forth. So the total distance doesn't care if you're going back and forth. It just wants to know how far you walked. So so the difference is then for the total distance, then you have to add up all the parts. That is, you have to figure out in your function which part of your area under the curve is negative and make it positive, and then add it all up. You can't just integrate from beginning to the end, because then you will get a net distance. That is how far you've gone so far, not how far you've walked. You've maybe gone back and forth 100 times. All that has to be added up. So so to look at the graph for example 5.225, you see the graph on top, which is the equation that they graphed there, to show you there are two parts of this integration. So you have to take the trouble of figuring out when does the function cross the x-axis. That is, where does it stop being area stop being negative and become positive, and integrate from that part on. So the first part, you go integrate from 0 to wherever that is, right? And then the second part from that intersection point to the next part, so that you calculate the area of the two triangles, which is even more tedious than the previous problem, as you can see. Okay, look at all these numbers. But if you just keep track of everything, then the problem is actually very straightforward, if not completely tedious. So please do that. Do example 5.25 as part of your homework as well. Next, let's look at example 5.26 about, well, if the motor on the motorboat starts at time equal to 0 and the boat consumes gasoline at a certain rate, which the rate is the derivative, okay? And then we want to know how much gasoline is being used. In that case, you integrate. The integral of the rate becomes the total area under the curve, which in our case is the total gasoline that's being consumed. So then the question asks you about the first hour. So you're integrating from 0 to 1. What? Yeah, that's right. So you're integrating of using the power rule. Is a simple power rule situation. So you integrate with the power rule, and actually the answer is fairly straightforward. So please do this one as your homework as well. And next we are going to look at something called ice boats. Now, I normally don't care about the weird applications that your book have a tendency to pull out of their hats, but the ice boat, that's worth mentioning, because it says right here that the ice boats run on wind, okay? And they like little skates that they sit on the frozen lakes, huge frozen lakes, and they can sit on their little skating boat, right? And they're sitting on the ice, and then they use sails like a sailboat to help them move, which makes perfect sense, right? But here's what's weird, okay, that I haven't figured out, and I've given it some thought. It says that these things can go, they sail by wind force, obviously, so they can go as fast as the wind. But here's what's weird. They can go faster than the wind. And not just a little bit faster. They can go a ton faster, something about 5 times faster. That is weird from a physics point of view. Like, how in the world can it possibly go 5 times faster? In other words, if you have a wind blowing at 30 miles an hour, that boat might be going 150. I mean, it's like, is this for real? It doesn't make any sense. Like, what can possibly be making it going that fast? Nevertheless, well, I haven't figured it out yet. Okay, there's an explanation online that doesn't make any sense to me. But there's no way I can deny the truth. What's the truth? The truth is this thing is going faster than the wind can blow, which I didn't think that was possible. But who am I to argue against reality, right? Reality is this thing is going fast. It's shooting along like a bullet. Imagine 30-mile wind, which is a pretty breezy wind, but it's no hurricane. Whereas if you're going 150 miles an hour, that's a hurricane speed. So it's very, very impressive. But anyway, so there's this ice boat, and whether it's an ice boat from a mathematical point of view, we don't care if it's an ice boat or whatever it is, right? It's just traveling at some distance, and what are we trying to do? how far he has traveled or something. And I think he is traveling in the same direction the whole time, I believe. So you just integrate, and his traveling speed is given by two equations, which is fine. You just integrate each equation for each part of the time, and then come up with some solution. So again, is maybe a bit tedious, but at least straightforward. So please do that as your homework as well. Example 5.27. Now continuing, let's look at the next rule on page 572, odd and even functions. The thing about odd and even functions is they have that interesting characteristic such that, for example, let's consider an even function, x squared. Even function just means is the same left and right, mirror image of each other. So then if you were to integrate from the exact same spot, such as minus a, okay, and then the positive a, then the area under the curve will be exactly the same because they're mirror images of each other. And therefore, when you integrate like this, all you have to do is just integrate from 0 to a, okay, the function f. There's f. And then multiply by 2, add it up, and that's your resulting integral, which might save a little bit of time. Or if you do integrate from minus a to a, you will soon notice that plugging in minus a down here in your evaluation formula gives you the exact same answer. Well, it's the same. So then you don't have to evaluate. Well, yeah, you just copy the same thing twice or something. So then, so either way, you're going to realize that, okay? If you integrate a even function, it's because it turns out to be the same when you evaluate top or bottom. So, and as a result, to integrate an odd even function, you just is double of integrating from 0. If you're integrating from the exact same point, that is from negative a to a. If you're integrating some other point, then of course none of this matters. But at the exact same point, then the two chunks of area you're integrating are exactly the same. Now the same thing can be said of the odd functions. I mean, not exactly the same, but a similar situation. That is, for example, if you have to integrate, this is x to the power 3, and y equals x3. Now in that case, your integral is again identical. This is exactly the same as that. And then you're integrating from minus a to a again. Now in that case, however, the area, while the area is exactly the same, this area is negative. So when you integrate an odd function, it will end up being 0 because you just subtracted this one out exactly. So for the odd function, the integral from exactly minus a to a will become 0. And this is not much of a rule. I mean, you realize that when you try to do it, that your solution will come out to be 0. All right, and then so having said that, let's look at some example. What is this? Example 5.28. You integrate an even function that is just a polynomial, straightforward using the power rule, and then grind through the integration. And and then you come up with some answer. And then so please do example 5.28 as well as 5.29, which says that you're integrating an odd function. Is that thing odd? Yeah, it is. Okay, you integrate an odd function and end up being 0. See? And yeah, if you realize that the function is odd, then you can just say it's 0 without doing any integrating. So please do example 5.28 and 29 as your homework. For homework, please do on page 575 problems 207, 209, 211, 23, 27, 29, 41, and 43. And I want to talk about problem 241, and I will do so after you get your homework done. Problem 241, which is, well, anyway, let's look at problem 241. Sandra is some 25-year-old woman who weighs 120 pounds. I don't think that's relevant to our mathematical concerns. She burns 300 minus 50 T calories per hour. That's a rate, okay? So remember that, and we're about to integrate it somehow. While walking on her treadmill, fine, her calorie intake from drinking Gatorade is 100 times T calories during the Tth hour. Okay, so okay, all right, that's the calorie intake, fine. What is her net increase in calories after, net decrease in calories after walking 3 hours? All right, so we have two situations happening here. One is she is walking, which means, and she's walking and burning something like 300 minus 50. All right, so that's the burning of the calories, so that's negative 241. She's burning, let's see, 300 minus 50 T. And that's a negative value because it's decreasing. Okay, she's burning calories on the treadmill, and then she's adding her calorie intake by drinking Gatorade, which is adding 100 T. Yeah. Anyway, so her drinking of the Gatorade is, well, we don't care. Okay, the point is that's what's happening. And then we have to calculate the total result after 3 hours. So we are going to integrate from 0 to 3, the first 3 hours, and then dt. All right, so that equals to, let's see, that equals to, that's just t, and why do I have, okay. Well, anyway, so well, let me show you what I did, okay? That is, it also shows you what I did in the previous problem, 229 and then 243, which I just pulled out the answer without doing any integration. Yeah. But anyway, 241, all we get is I draw the graph. I'm not sure if I should show you how to integrate or show you just do the graph. Let's do the graph because it's more fun, even though we're not doing, strictly speaking, integrating. So what's happening here is that this whole thing becomes 300 minus 300 plus 50. Okay, so you have minus 300 plus 150 T. That's the, oh, that's why I don't know what I'm saying. And then why am I puzzling over this? The graph I have is fine. And the point is that you can just integrate this thing, right? Or, but I did something like this. I drew the graph of the minus 300 plus 150 T, where you have, is that word? I'm puzzled as to whether I should show you what I did versus just have you integrate it the old-fashioned way. And so I will just show you what I did, I guess, just for the fun of it. So this is minus 300 if you draw out the graph. Oops. So by the graph, there's minus 300, and then this is 1, 2, 3. Okay, when the t is 2, this is 0, and then the top height is 150. And so as you can see, this is 1 and this is 3. As you can see, that this area here cancel out with this area. This is gone. So the net integration, which is a negative area, it goes from, this is minus 150. Okay, so the area where the integral is just this area down here, which is negative, and which is a trapezoid. So we do the trapezoid formula, which is the top plus the bottom times the height divided by 2, so the integral equals to the 150, okay, plus 300 divided by 2 times the height, which is just 1, and divided by 2, and the whole thing is negative. And that gives us minus 225 calories, which means the woman is losing 225 calories per hour or something. No, the total number of calories is she lost, period. After working out for 3 hours, she only lost 225 calories because she's drinking Gatorade. I guess that's the moral of the story. Yeah, and of course you don't have to pull off that thing. I don't know why I did that, but that's what I did. so I thought I would just show it to you for the fun of it. You can just do the regular integration. Okay, it's just a very simple line, and the integration is also straightforward and probably just as fast. Now, having said that, that's the end of this section, and I want to talk about my literature recommendation again. I haven't said that for a while. The last time I recommended that you should listen to Shakespearean professors' lectures. That just find some of them online, doesn't matter which one, and listen to them, and they are tremendously fun. The next one I want to recommend for this course, for literature, that has nothing to do with calculus, is to read the complete collection of Sherlock Holmes. Okay, which is by Sir Arthur Conan Doyle. These books you can get them downloaded for free, or you can just buy a copy hardback if you prefer it that way. Either way, they are the Sherlock Holmes stories in the past, and I think it's written in 1800s or something, is it was such an international sensation that it was similar to the Harry Potter of today, I would say. And yeah, of all the books in the past that just blew the world out of the water, Sherlock Holmes is definitely one of those. So I highly recommend that you read them. And then afterwards, there's also a TV show currently called Elementary, which is based on the Sherlock Holmes story, but is completely in the modern setting, and is very, very different. You just have it carves a new path for Sherlock Holmes. And that one is also pretty good that I've been watching lately, although it's not as good as the original Sherlock Holmes, obviously, but it has its own charm. And then that's by no means the only one. There are many Sherlock Holmes movies and TV shows and whatever and I've seen some of them, and they're mostly very, very good. So I do recommend, if you haven't read the complete Sherlock Holmes, that you absolutely should do so. As a calculus student, yeah, I think calculus students should know Sherlock Holmes. Have read it. The complete collection might sound like a lot, but you don't have to read them all at the same time. They're just individual short stories. I don't remember how many there are, but there's a big pile of them, and they're very, very cool to read. Okay, so please read complete Sherlock Holmes in your spare time.